In today's episode of the Daily AI Brief, we'll explore advancements reshaping the landscape of AI technology. From text to SQL models redefining database interaction to the significant push towards open standards in AI, we've got a packed lineup. Here's what's on the docket for today's discussion. Imagine querying databases effortlessly using natural language without losing context. Feyn AI's new SQRL models have made this future a reality. These text-to-SQL models are designed to inspect the database schema before crafting queries, making database interactions smoother and more accurate. This enhancement addresses the notorious ambiguities usually seen in similar systems. So what sets SQRL apart? It's built on a transformer architecture fine-tuned for SQL generation. Here's a quick breakdown. The models inspect databases, understand schema structure, and adjust queries accordingly. They employ natural language processing for cleaner user query interpretation. Read-only probes ascertain schema layout, ensuring query accuracy. Fine-tunability allows adaptation to various databases for even greater precision. The technology allows SQRL to achieve impressive performance. The flagship model, SQRL 35B-A3B, distinguishes itself with a 70.6% execution accuracy on the BERT Dev benchmark, significantly ahead of its competitor, Claude Opus 4.6, which scores 68.77%. Remarkably, the 4B and 9B versions provide nearly equivalent accuracy, which facilitates deployment in resource-constrained settings without sacrificing too much precision. Practical steps for utilizing SQRL involve accessing the models on platforms like Hugging Face. Users can fine-tune these models according to specific database schemas, optimizing their performance, and replacing traditional SQL query generators within existing systems. Additionally, conducting tests on a range of datasets can ensure that the models consistently meet accuracy standards across varied applications. Despite its strengths, SQRL also presents certain challenges and limitations. Its effectiveness on real-world databases with complex schema structures is still untested. There are concerns about the model's latency under high-demand scenarios, especially in environments requiring rapid query processing. These factors necessitate careful consideration when deploying SQRL in commercial systems. In conclusion, Feyn AI's SQRL represents a significant leap in creating more intuitive and effective SQL queries through AI, promising a future of seamless database interactions. By minimizing ambiguity and enhancing execution accuracy, it paves the way for more accessible database management, potentially extending the reach of SQL-driven insights to a broader, less technically inclined audience. OpenAI's recent update to its Codex model has stirred quite a buzz in the developer community, and not necessarily the good kind. The context window for the new GPT 5.6 model has been slashed from 372,000 to 272,000 tokens, which many devs feel cramps their coding efficiency, especially on larger projects. Why does context matter? Essentially, it defines how much information the model can process in a single interaction. A larger context can manage sprawling codebases more effectively. The main points include contextual constraints. With the reduction to 272,000 tokens, developers now face a tighter constraint on how much source code and associated documentation can be fed into Codex simultaneously. This can stymie attempts to leverage the model for extensive code reviews or during complex debugging sessions. Pricing concerns. Breaching the new token limit introduces steep cost implications, with double pricing on inputs and 1.5 times the cost on outputs. This presents a significant financial consideration, especially for small to medium enterprises or independent developers operating on tight budgets. OpenAI's nebulous pricing communication only exacerbates these concerns. Impact on workflows. For developers accustomed to a 372,000 token buffer, this cut can disrupt established coding workflows, especially those involving intricate multi-file projects. The reduction necessitates a strategic reevaluation of how code snippets are structured and processed to avoid unintentional costs. Technical integration challenges. The adjustment complicates API integrations. Many integrated development environments, IDEs, currently do not alert users when approaching the token limit. Developers must now rely on proactive monitoring and possibly seek plugin extensions or tools that provide such notifications. To mitigate challenges, developers might consider several practical approaches. 1. ID adjustments. Check whether your IDE has or can be equipped with plugins that alert you to token threshold breaches. This can prevent unexpected charges by enabling preemptive adjustments. 2. Code segmentation. Reassess how projects are segmented. Smaller, more frequent requests could help manage token utilization within revised limits, ensuring uninterrupted operation without hefty financial penalties. 3. Community engagement. Engage with fellow developers in forums to share strategies and tools that accommodate the new constraints effectively. Shared experiences might reveal alternative approaches or community-devised solutions to manage context limitations. 4. Review documentation. Regularly review OpenAI's API documentation for updates on managing context limitations and pricing changes. Staying informed can offer a competitive edge in adapting workflows swiftly. OpenAI's decision, perceived as a necessary trade-off for perhaps underlying technical requirements or cost optimization, still leaves room for concern among developers. Without clear communication on underlying reasons, it's hard to appease a community that depends heavily on these capabilities for efficiency and cost-effectiveness. Competitors offering larger contexts might now look more enticing to those feeling the pinch, suggesting this move could have broader implications for OpenAI's market position in the AI development space. NVIDIA's NVLink technology is revolutionizing GPU-to-GPU communication within AI factories, allowing data centers to benefit from high-bandwidth, low-latency communication between NVIDIA GPUs and partner CPUs, like those from ARM. This advancement is instrumental in meeting the growing demands of large-scale AI workloads by optimizing performance and improving operational efficiency. One of the core features of NVLink is its architecture, which is designed to integrate seamlessly into existing data center setups. It leverages advanced networking architectures to boost data transfer between GPUs, making it superior to traditional methods. This technology supports multiple GPU configurations, ensuring high throughput and efficiency, which is critical for handling demanding AI tasks. The promise of real-time AI inference tasks highlights its potential to process large datasets swiftly, although exact bandwidth figures remain undisclosed. NVLink's design incorporates Ethernet technologies, enabling it to efficiently connect multiple GPU nodes and facilitate a cohesive networking solution. This aspect is particularly valuable for enterprises aiming to build customized AI infrastructures. The scalability and robust integration capabilities make NVLink a desirable option for those seeking to reduce development times and complexities in AI research and application. Investments in companies like Marvell significantly enhance NVLink's ecosystem. A $2 billion investment supports the development of custom silicon solutions, ensuring compatibility and performance optimization. Such collaborations extend NVLink's capabilities, potentially creating semi-custom AI solutions best suited for specific procedural needs in diverse fields. Despite these promising attributes, the technology faces challenges. The effectiveness of integration significantly depends on supporting a range of CPU and GPU configurations. Successful implementation requires optimized configurations that may not be achievable for every user, posing a risk for widespread adoption. Additionally, NVLink's market positioning against competitors like AMD and Intel remains an area to watch. For those interested in implementation, NVIDIA's NVLink Fusion page provides detailed guidelines. Reference architectures offer further insights into setting up AI factory infrastructures, aiding developers and enterprises in leveraging NVLink's full potential. NVLink represents a significant step toward evolving AI infrastructures with the capability to accelerate AI application development timelines globally. As NVIDIA continues to innovate in GPU communication technologies, it aims to solidify its leadership in AI data centers, driving forward both technological advancement and competitive dynamics. Moonshot AI has made significant waves in the artificial intelligence landscape with the unveiling of the Kimi K3 model, a gargantuan AI tool boasting 2.8 trillion parameters. This monumental release positions it as the largest open-source AI model to date, setting unprecedented benchmarks in AI development. Why is Kimi K3 groundbreaking? A key feature of Kimi K3 is its open-weight architecture, designed to enhance accessibility for developers and research teams across the globe. This architecture allows users to freely download and modify the model, encouraging a culture of innovation and collaboration within the AI community. The model's open nature significantly lowers the barriers to entry for cutting-edge AI technology, enabling more inclusive research and application development. The model incorporates advanced methodologies like the mixture of experts, MOE, a technique that improves the model's efficiency by dynamically routing information through different subsets of the model's layers. This, coupled with sophisticated tensor processing techniques, allows Kimi K3 to perform complex calculations quickly and accurately, proving highly beneficial for tasks such as large-scale data processing and real-time analysis. Furthermore, Kimi K3's API integrations make it easily adaptable across various programming environments, fostering versatility in application. Developers can seamlessly integrate Kimi K3 into existing workflows, enabling rapid prototyping and deployment of AI-driven solutions. Challenges and considerations. Despite its record-breaking scale, several challenges accompany the Kimi K3's launch. Independent verification of its performance and parameter claims remains crucial, as such claims are currently based on in-house tests. Additionally, the model's immense size may necessitate substantial infrastructure, potentially limiting its deployment in resource-constrained environments. Initial performance evaluations have indeed spotlighted its exceptional ability in front-end coding sectors, but these need broader validation. Moonshot AI has also faced logistical hurdles, temporarily halting new subscriptions because of overwhelming demand. This stoppage highlights the limitations in service capacity and reflects the necessity for strategic scaling to support an ever-growing user base. Opportunities for exploration. For those interested in delving deeper into Kimi K3's capabilities, Moonshot AI's official webpage and GitHub repository serve as valuable resources. Developers and researchers can access detailed documentation, implementation examples, and integration tips, allowing for real-time experimentation and understanding of the model's vast potential. In conclusion, the launch of the Kimi K3 model signifies a milestone in Moonshot AI's journey to redefine open-source AI technology. By facilitating greater access and utility in AI development, Kimi K3 not only underscores Moonshot AI's pioneering spirit, but also marks a significant advance in the global AI landscape. NVIDIA has partnered with Hugging Face to roll out NeMo Automodel, a toolkit aimed at simplifying the training of diffusion models, targeting the needs of AI developers and researchers. As the complexities in AI modeling grow, the importance of tools like NeMo Automodel cannot be overstated, especially in enhancing the training and fine-tuning processes crucial for the next wave of AI model innovations. The unveiling of NeMo Automodel marks a significant advancement in the training landscape for diffusion models. This toolkit, which integrates seamlessly into Hugging Face's diffusers library, offers a robust solution for integrating complex model functionalities with efficiency and precision. It builds on NVIDIA's established expertise in model development and the transformative capabilities of the Hugging Face ecosystem. One of the standout features of NeMo Automodel is its support for multiple parallel strategies, including tensor and expert parallelism. These strategies are critical as they allow the distribution of computational tasks across different resource allocations, effectively reducing the bottlenecks typically encountered in large-scale model training. The incorporation of deep EEP and transformer engine kernels further enhances training throughput, optimizing performance significantly by improving the processing speed and efficiency. Technically, NeMo Automodel is a PyTorch native training library, which streamlines interactions with Hugging Face's transformers. This integration enables users to load models easily and leverage existing frameworks, making the toolkit highly accessible for those familiar with PyTorch and Hugging Face. The presence of YAML configurations also simplifies the process of launching model training sessions, allowing users to hit the ground running with initial experiments. In practical terms, developers can explore the NeMo Automodel by diving into detailed documentation provided by NVIDIA, which offers comprehensive setup instructions and insights into leveraging Hugging Face's training guides. This hands-on experimentation is vital, for understanding how to tailor the toolkit to specific project requirements and unlocking its full potential. Despite its promising features, there are trade-offs and limitations to consider. The full range of diffusion models supported by NeMo Automodel isn't clearly outlined yet. This lack of clarity may introduce challenges when it comes to runtime compatibility and scalability across diverse architectures. Furthermore, users might face hurdles regarding feature compatibility, especially when integrating NeMo Automodel with pre-existing model frameworks. The implications of NeMo Automodel could be transformative, making advanced AI training strategies more accessible across various industries. By facilitating efficient image and video generation, it can accelerate research and development cycles, while potentially inspiring further collaborations between NVIDIA and other platforms. In essence, NeMo Automodel represents a vital step forward in NVIDIA's mission to democratize AI training technologies, extending capabilities to developers worldwide and simplifying the integration of advanced AI models in real-world applications. While questions remain about the broader acceptance and the specifics of model support, the toolkit signals a progressive move towards more streamlined and powerful AI development processes. OpenBMB's Mini CPM 5.1b marks a significant advancement in AI technology, specifically tailored for local deployment to enhance privacy and reduce latency. Let's explore how this model is poised to transform device-specific AI integration and operation. Mini CPM 5.1b features an impressive 1.08 billion parameters, designed to work seamlessly on entry-level devices such as phones, laptops, and even web browsers. This substantial parameter size allows for complex language understanding and generation tasks, providing a more robust user experience directly from local machines. One of the key strengths of Mini CPM 5.1b is its extensive context window, which holds up to 131,072 tokens. This capability supports the model's superior handling of nuanced language tasks, such as code generation and reasoning. Specifically, it scored a remarkable 17.9 on the Artificial Analysis Index, outpacing other models like Qwen 3.5-2b, which achieved a score of 16.3. This demonstrates its leadership in efficiently managing context-rich tasks, which is particularly beneficial in applications demanding extensive comprehension or intricate response construction. A pivotal feature of Mini CPM 5.1b is its local deployment architecture, which significantly reduces dependency on cloud infrastructures. This architectural choice enhances real-time processing capabilities, drastically improving latency when compared to traditional cloud-based models. This shift not only bolsters user privacy, as data processing occurs locally without transmitting sensitive information over the internet, but also enables offline functionality, a valuable advantage in areas with unstable internet access. The open-source release under the Apache 2.0 license empowers developers with access to the model's weights, training data, and code. This openness fosters an environment where innovations can flourish, with the community able to adapt and expand the model to suit specialized applications. For instance, developers can fine-tune Mini CPM 5.1b using available agent skills and customize it for domain-specific tasks, leveraging detailed cookbooks and guide to facilitate seamless integration into local systems. While the model's capabilities are promising, there are considerations regarding hardware compatibility and optimization for lower-resource devices. Although it is designed for broad device support, ensuring that it performs optimally across all intended hardware configurations remains a key focus point. Moreover, while the benefits of local operation are evident, the model's performance and feature set might still reveal limitations when compared to comprehensive cloud solutions. For those interested in exploring Mini CPM 5.1b further, the source code and pre-trained models are readily available on GitHub and Hugging Face, respectively. Step-by-step deployment guides and usage examples are provided to assist users in harnessing the full potential of this local AI model. As the trend toward local AI solutions accelerates, Mini CPM 5.1b stands out as a pioneering model that balances sophisticated AI performance with the growing need for privacy and offline capabilities. By empowering developers and enterprises to customize AI solutions directly on devices, it sets a new standard for AI accessibility and utility in everyday applications. In a profound shift within the artificial intelligence industry, major AI companies such as Anthropic and Google are increasingly prioritizing open standards over the traditional model of competitive secrecy. This evolution marks a strategic pivot towards fostering interoperability and collaborative innovation, evidenced through meaningful contributions of key technologies to the Linux Foundation. Key developments. One of the most notable initiatives in this direction is the formation of the Agentic AI Foundation, AAIF. Co-founded by Anthropic, OpenAI, and Block, the AAIF aims to create a neutral, interoperable infrastructure for AI agents, emphasizing openness and community-driven governance. A cornerstone of this initiative is the Model Context Protocol, MCP, an open-source protocol contributed by Anthropic. The MCP is designed to be vendor-neutral, a crucial aspect that ensures that the technology remains accessible to a broader community, enhancing opportunities for innovation and collaboration. Currently, more than 10,000 active servers utilize the MCP, showcasing this protocol's vast adoption and the potential for expanding collaborative frameworks globally. In tandem, OpenAI's contribution of the agents.md documentation to the Foundation underscores the commitment to create standardized protocols that simplify the development and integration of AI agents. Agents.md, now used by over 60,000 open-source projects, provides comprehensive guidance that helps developers build more sophisticated and interoperable AI systems. Challenges and trade-offs. Despite the promising outlook of these initiatives, several challenges linger. The effectiveness of open standards largely depends on widespread industry adoption and the seamless alignment of open collaboration with proprietary business interests. This balance is often tricky, as fostering an open community can sometimes clash with the need to maintain competitive advantages. Additionally, there is a risk of fragmentation during the transition from proprietary models to open standards, which could potentially slow down innovation cycles. The industry must also address the potential limitations associated with over-reliance on community-driven processes, which, while promoting inclusivity and transparency, may hinder rapid responsiveness to technological advancements and market demands. Looking ahead. For individuals and organizations keen to engage with these developments, practical steps include exploring resources on the Agentic AI Foundation's official website and participating in open-source projects that utilize the agents.md documentation. This engagement not only provides insights into the practical applications of these standards, but also supports community development and knowledge sharing. The shift towards open standards reflects a broader realignment in AI development priorities, from fierce competition in proprietary advancements to a collaborative ecosystem driven by shared goals and transparent progress. As this movement gains momentum, it could lead to a more unified AI ecosystem, fostering an environment where innovation flourishes and interoperability minimizes frustrations associated with multi-vendor environments. Although the timeline for the general adoption of these standards remains uncertain, the foundational work being carried out today is likely to pave the way for significant breakthroughs in AI collaboration and usability. That's all for today's episode. We've delved into fascinating AI advancements and the push towards open standards that could reshape the industry landscape. Remember to dive into these topics further through the resources shared today. Join us next time as we continue to explore the ever-evolving world of AI.